All right, moving on to Chapter 22, what we are going to do in Chapter 22 is talk about the derivatives of functions that are not polynomial functions. And Chapter 22 focuses on the exponential and logarithmic functions. So we're going to talk today about the derivative of e to the x. Well, that's the easiest one to remember because the derivative of e to the x is e to the x. So everywhere on this graph, the curve, or the y value on the curve, is the same as the slope of the tangent line at that point. So it's kind of an easy rule to remember. Of course, the product rule and the quotient rule and the chain rule still apply, so let's just do an example so that we can see how we would do this. All right, I've got a function here, y equals e to the 7x plus x squared times e to the root x plus e to the x squared plus 9x. All right, well, in each case, I've got either a chain or a product or something that I've got to do. So in this first term, e to the 7x, the outside term is e to the something. And we've already said that the derivative of e to the something is e to the something. So I will say that that is e to the 7x. All right, and that takes care of that part. Then I say, what is the derivative of 7x according to the chain rule? And that would be 7. So there's the derivative of the first term. In the second term, I've got a product, and in the second part of that product, I've got another chain rule. That's e to the x to the 1/2. So product rule says take the derivative of the first, which is 2x, times the derivative of the the derivative of the first times just the second one, which is e to the root x, plus the first, which is x squared, times the derivative of the second. So that's going to be where the chain rule comes in. The derivative of e to the something is e to the something. And then I take the derivative of the something, which in this case is root x, or x to the 1/2. And the derivative of that is 1/2 x to the negative 1/2. That takes care of that. Then for the last term, I've got another chain rule. The derivative of e to the something is e to the something. So e to the x squared plus 9x, that whole thing is an exponent. So that takes care of that. Times the derivative of x squared plus 9x, which would be 2x plus 9. Alright, so before I simplify, that's basically what I get, and hopefully that matches up with what I wrote down. Alright, and then if I need to, I would simplify it. I bring the 7 out front. What else did I do? I brought the half out front, and then I combine this x squared and this x to the negative 1/2 to make x to the 3/2. I distributed the e to the x squared plus 9x to both of those terms, and I just made it look a little bit nicer. Alright, and really nothing's changed. You just have one new rule to add to your list of rules, and that is that the derivative of e to the something is e to the something times the derivative of that something. Or if it's as simple as e to the x, then the derivative of e to the x is just e to the x. Alright, so that's where we stop, but for those that want a proof that this is actually true, you can keep going. If you're not that interested in the proof, you can stop here, but the rest of us will keep going. So here's our proof. Let me just do this step by step. Alright, so we're going to start off, there's f of x, it's e to the x. And we're going to use our limit definition of what the derivative is. The derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Alright, so using this as our f of x, this is what we get. F of x plus h is actually e to the x plus h, and f of x is just e to the x. Alright, and if I write e to the x plus h a little differently, I can write it as e to the x times e to the h. And now what I notice is there's a common factor in the numerator of e to the x, which is not dependent on h at all. So I'm just going to pull it out. And what I'm left with is, after I factor out this e to the x, I'm left with e to the h minus 1 all over h. Well, I still can't plug in 0 for h and get anything other than 0 over 0. And I can't do anything algebraically to make it look any nicer. So what I'm going to do is I'm just going to look at a table of values. Okay? I'm going to try a bunch of h's that get close to 0 and see what happens to e to the h minus 1 all over h. Well, when I try negative 0.1, I get 0.9516. And when I try negative 0.01, I get 0.995. When I try negative 0.001, I get 0.9995. I think we see where this is going. At 0, I get 0 over 0, which is a determinant. And then let's look at what happens when I go to the positive side. I get numbers like 1.05, 1.005, and 1.0005. So you can see that the function doesn't exist here, but the numbers actually approach a y value or an h or a value of 1. All right, so we can say that the limit equals 1. Okay, so here's the limit, and I just said that that's equal to 1 based on what I saw in the table. So e to the x then times this thing that's equal to 1 is just going to equal e to the x. So the derivative of e to the x, by the formal definition of what derivative is e to the x. All right. The other proofs in this section won't be as detailed because this proof is going to help us find the proofs for the other derivatives. So if you have any questions on that, please email me. Otherwise, I'll see you tomorrow.